Good morning, friends. So today again we are going to discuss the same topic. If you clear, no problem. If you have doubt, again you can go through this. Okay? Because this is very important. One problem in graphical method definitely will come. You have to follow the same sequential step. Okay? You know, the inertia forces in connecting rod we are going to incorporate in this calculation along with the weight of the connecting rod. In the earlier analytical method we didn't bother about the weight of the connecting rod and inertia forces of the connecting rod and crank. Okay, so here we have to consider the inertia forces of the connecting rod. So we have to find out direction through which the force that will be acting, that inertia force, and also the magnitude of the inertia force we have to calculate. Fc component we have to calculate. So for that we are using Klein's construction. You know the procedure to find out, or instead of drawing velocity and acceleration diagram separately, we can use this Klein's construction. The same space diagram itself we can find out velocity and acceleration diagram by drawing velocity and acceleration polygon in the space diagram itself. Consider the 4-bar mechanism. Is it visible to the laws? Okay, so for a crank angle that is given, maybe theta is taken, certain degree, 30 degree or 40 degree or 45 degree. At this position, we have to find out what will be the component, that is inertia force component. With respect to this position, we have to calculate all the component, Fi, Fp and also Fc, okay, Fr, Ft, that all. So this is named here OCP. P is a piston, C is a crank pin, this is a O is a crank shaft, this is theta. To obtain Klein's velocity diagram, you have to extend the connecting rod, okay, up to M. You can have a triangle from OCM. So just we have to extend this and you have to draw this. Okay, so you can get a triangle OCM. This reflects the velocity diagram which obtained from the velocity, okay, velocity polygon. OCM reflects the O1, O dash or A dash, O dash, C dash, M dash. Okay, so the crank velocity, connecting rod velocity, and the resultant, that is line of stroke, can be calculated by using this. So after that, what you have to do? After that, next step, you have to draw the circle. Take CM as radius, you have to draw one circle. Okay, so C as center, CM as radius, you have to draw a circle. Then you have to draw another circle by taking connecting rod as your diameter. Okay, so you know connecting rod length which will be given in the problem. If you know the connecting rod length, you have to draw it. In your while solving, if the space is not enough, you can take a suitable scale. If it is given 1200 mm or 1500 mm, you can take a suitable scale. By reducing all the dimensions to a scale, we can draw this. Okay. Any doubt in this? Up to this? So then the intersection point, the large circle and small circle intersects at 2 points. That point is named here as K and L. Okay, so what you have to do next? Join K and L and extend up to the line of stroke. KL and extend up to the horizontal line. That point may be named as N. Okay. After that, you have to name the intersection point. It cuts the connecting rod or the line along the connecting rod at Q. So now you have a polygon, okay, CQNO. This CQNO gives the acceleration diagram. Instead of, if you draw a separate acceleration diagram, that reflects the same shape. Okay, so this gives you the acceleration polygon, by using which you can calculate acceleration of the crank, a radial component of acceleration of the connecting rod, tangential component, by using which you can find out the resultant acceleration. That gives you the acceleration of the piston with respect to C, that is connecting rod or crank pin. Okay, and finally you can get the resultant line, that is given here by NC. So you have a N and you have a C, you have to join these two. Okay, you have another line here. CQNO gives the acceleration polygon. So up to this is a Klein's construction. By using the triangle CMO, you can get the velocity, all the velocity value you can calculate, and by using the value CQNO, you can find out the acceleration. Okay, so after that, what you have to do? The inertia force, that is Fi, that component we know already, so that you have to mark it down here. This is Fi, inertia force. Then you have to find out the center of gravity point. Why we have to consider here? The connecting rod is a rigid body having a, it's not a uniform cross section. Okay, so we have the load or the solid material or weight may be concentrated in different places. So we have to consider, or we have to solve by using a dynamical equivalent problem. So the entire mass of the connecting rod may be divided into two masses, that is concentrated in 2 points. One is at a piston, that is here. One is concentrated at one end, that is at piston. Another one where it is concentrated, that we have to calculate. We have already discussed by using a relation L1 L2 is equal to K square. If you know K, that is radius of gyration, directly you can find out the point where the second mass is concentrated, that is D. Otherwise, one more method is there. You have to find out the point Z by drawing a perpendicular line from G. So draw a line perpendicular to Z. So you have to fix the point Z. So how you can fix? We already noted down that Z should be equal to K. This is the relation. K is the radius of gyration that you can calculate from the formula. If the mass moment of inertia is known, you can find out. Otherwise, how you can find out? Other than this, by considering the connecting rod as a compound pendulum. Okay, so from the compound pendulum formula, you have to find out the time period. From the time period, if you substitute, if you know the time period for oscillations, you can calculate K value. So there are three methods. By using this, you can find out K. Okay, if K is unknown, some relevant data will be given. So based on the data, you have to find out K. Either I will be given or some time period for oscillations will be given. So you have to consider it as a compound pendulum. So using that formula, you have to fix this. So then Z is equal to K. So you have to fix the point Z here. Okay, then join PZ. So this is our Z. Join PZ. Okay, so right angle to this line, okay, or 90 degree for this line, we have to make another line which makes 90 degree. It cuts the connecting rod line. So that point you have to take it as D. So this is a point where the second mass is concentrated. Okay, so the second mass with respect to the force or for this position, the second mass is concentrated on D. So the entire mass of the connecting rod, it is not located on the crank pin. The load is concentrated on the point D. With respect to this point, you have to calculate the inertia force. Clear? So we have already calculated or we already drawn the acceleration diagram in terms of CQNO. The resultant is Cn. Okay, so we have to find out what will be the acceleration at point D. How you can find out? Suppose I have a acceleration diagram here. So roughly I drawn some diagram. Assume that this is an acceleration diagram. Okay, this is O, this is crank C, this is radial component, this is tangential component of the connecting rod. So this is acceleration of the connecting rod. Okay, so this is acceleration of the crank. Crank may be taken as C. This is B with respect to C. This is B with respect to O. So assume that this is a acceleration diagram for the space diagram which is given. Okay, you know the point G. How you can calculate the acceleration at point G? Yeah, last semester you studied by using the ratio, the length ratio. Okay, that is PG, PC. Okay, PC divided by PG is equal to this Cn, that is the resultant. Maybe this may be taken as S. This distance. So PC divided by Cs is equal to the ratio. PG is equal to unknown point, some unknown point. So we have to find out unknown point. All other value can be calculated. So by using this relation, we have to find out the unknown point. Not only the point G, suppose you know the point. If you want to calculate the acceleration at this point, take the ratio. PC, suppose if this is to be taken as G, PC divided by PG or PC divided by this value. Okay, or PC divided by this value should be equal to Cs divided by this ratio. So unknown value you can calculate. This is the way you can calculate the unknown point in the acceleration diagram. So in that acceleration diagram should be equal to the accelerations which is acting at the point. So instead of this polygon, this Nx Cx is equal to Cn. Okay, we have already formulated the point D. So how you can calculate here? Instead of drawing separately, instead of using this ratio, what I can do, because both are in the same diagram. So what I am doing, from G, I extend up to this line. Okay, parallel to this line of stroke. Okay, so extend one line from G, which cuts the Cn at one point, that should be taken as small g. From D, extend a line, it cuts the line at small d. Okay, so join OG and OD, that should be equal to the vector distance of an acceleration. Okay, so if you measure OG divided by the distance between PG or the distance between CG divided by the distance if you put, you can get the acceleration. Clear or not? It's a late pickup. Huh? So there are so many faces are sleeping. Yes sir, that's all. Huh? Have you understood this point or not? Okay. Otherwise, assume like that. Draw the diagram separately. So this is an acceleration diagram. Ignore that C, Q, and O and all. Okay, ignore that diagram. So you have drawn this diagram. You have to draw this again by using that procedure. Okay, you know this is a velocity of the acceleration of that band. There is no angular acceleration. So this is radial component of the connecting rod. This is tangential component of the connecting rod. This is the resultant Cx. So that should be equal to Nc there. Okay, use the relation or use the ratio between. We have to find out Pc divided by Pg. Pc you know, Pg you can calculate should be equal to the distance between Cx divided by the unknown point is small g. Assume that the point where you have to find out g. So you have to find out g. Okay. So you can calculate the value magnitude by using this formula or by using this ratio. Okay. That is similar length or similar triangle principle. The ratio between same side or same length or same angle. So by using that you can find out this. So what will be the direction? Our fixed point is O, join this G, okay. So parallel to this the line will be acting. Okay, so from that point where we are calculating the acceleration. Okay, so what you have to do parallel to this, you have to move from G, draw one line. So that will be the line of action of the acceleration. So we don't have the acceleration diagram separately. So that is there. This C point lies here. This X point lies here. Okay. This is horizontal. So this line is horizontal. So this is slightly inclined. So this is slightly inclined. So Cn is inversely there. Okay. So here, if you are not able to understand why we have to extend this line up to this point, what you can do, use the relation. Somewhere we don't know the G, we don't know somewhere, okay, so we have to find out the distance, use the same relation, Pc divided by Pg, that will be given in the problem. You can measure this height Cn, okay, by which scale you have drawn or you have taken. So from that scale you can fix this. This is unknown. You can calculate by using this ratio. Find out the distance from N or from C where you have measured the total distance. You can fix this point. Okay, if you take that or if you draw this, that should be lie on this parallel line. So that we have drawn a line parallel to this line of stroke. Clear? If not, again refer the presentation or refer the book. Okay, so you have to draw one line which intersects the resultant at G, small g. Okay, so we have to find out the direction. Magnitude you can find out, but we have to find out the direction. So that you have drawn one parallel line that intersects the resultant at G. Like that we have to find out the acceleration at point D. Okay, so that lies on G. Join OG and OD. So this OG vector or this OD vector, if you measure, okay, multiply with the scale, you can get the value in terms of meter per second square. Okay, because the acceleration polygon you have to draw by taking a scale. 1 centimeter or 1 mm is equal to this much meter per second square. So by multiplying that you can get the acceleration value. Clear? So that is the magnitude. The direction parallel to this, parallel to OG, the acceleration will be acting at point G. Okay, OD vector parallel to this OD, it will be acting at the point D. Clear? So we have to find out direction and magnitude. So by using this diagram, you can find out direction and magnitude. Any doubt in this up to this? Anybody who are sleeping there? Clear? Okay. Next thing. So we have find out magnitude. If you measure OG vector or OD vector or the distance, we can calculate magnitude. The direction is parallel to this. So we have to find out the resultant force where it is acting. We have used two masses. One mass M1 is acting at P, another one mass acting at D. Okay, both the point the acceleration will act. So the acceleration of the P where it is acting, in which directions it will be acting? Acceleration of the piston, line of the stroke. So it should be in a horizontal. So anywhere the acceleration is acting this direction. Okay, acceleration of the connecting rod, acceleration of the point D, where it will be acting? Parallel to OD vector. So take a scale, keep like this, move or parallel to this OD, draw a line from point D. Okay, it may go up or it may go down. Where it intersects at a one point, so that point is the intersection point. So what you have to do, you have to draw one line which intersects the line of stroke or which intersects the acceleration of P. So that is the point where the acceleration of both the masses. Okay, both acceleration intersects at one point, so that point is taken as E. So that point is the acceleration of both the masses. So we have to find out the resultant acceleration. The resultant accelerations where it will be acting? Parallel to OG with respect to the center of gravity point. Clear? Because OG is the line of action of the connecting rod. Entire connecting rod mass will be concentrated on G. So the acceleration is assumed to be acting at G. Okay, so we have calculated the magnitude and also we have calculated the direction if the mass is concentrated on G. So OG is the line of action. Okay, but the resultant must passing through E and it should be parallel to OG. So parallel to OG vector, from E draw one more line, that is the resultant force. Okay, so this force is to be considered as the inertia force of the connecting rod. Clear? This force will always act through E parallel to OG. Okay, since the resultant of the mass will intersect at point E, so that it will be considered as an inertia force in the opposite side. So that is the direction of inertia force, FC. Clear? So this is the direction opposite side. So you have to take or you have to consider this as the inertia force of the connecting rod. How you can calculate? Inertia force is equal to mr omega squared. Here m is mass of the connecting rod, r is the radius of the crank, omega squared with respect to the crank rotation. So by using this equation you can find out the inertia force. Okay, only the mass component differs. Mass of the connecting rod we have to substitute. Okay, so next we have to consider the inertia force of the crank. The inertia force or the force that are acting towards the crank is given by Fb, that is force acting on the crankshaft bearing. So the inertia force of that component will be acting in the opposite side, so that should be taken as Fr. Okay, why this Fr is used? This Fr may not be give any inertia force component, but this is used to find out the intersection point I. Okay, so that is instantaneous center. To find out that instantaneous center I, this component is used. Okay, so this will be taken as Fr, that is the inertia component which is acting opposite side of the crank force. Then we know the normal force Fn that will be acting here. So normal force, slide force will be acting this side. Yeah, this should be taken as a cylinder. It will be revolving or it will be acting all the directions. Okay, so both up and down the Fn will be acting. So we have considered one component in the upper side. So take Fn, the component will be acting at a vertical. So now both the Fr, both this Fn will meet at one point. Okay, so that point is the instantaneous center. Clear? So to find out that I, you have to extend Fr. Okay, so you have to extend at one point, that will be at this point. So this is Fn. So now what you have to do? Perpendicular to this Fc, we have to draw one more line which should meet the point I. We don't know the magnitude, only directions we have calculated. Okay, theoretically you can calculate based on the value of m or omega square, but practically how you can find out that value? Extend and draw one perpendicular line which should pass through I, so you can have the value. So that should be taken as x. Clear? So that angle should be right angle. Okay, so one component is over. Normal component we have taken, inertia force of the connecting rod we have taken, we have drawn the perpendicular distance Ix. Okay, for normal force we have drawn one vertical line, but we don't know the perpendicular distance with respect to the center point. Okay, so I and Fn both are acting in the same line, so there is no perpendicular distance. So Fn into the distance 0, so there is no force will be acting through Fn. So Fn is not considered. But Fi, where the connecting rod weight is acting at G. So you have to consider this weight also. Weight of the connecting rod that is acting at point G. So this is W. So from the W there will be some component will be acting upper side. So draw one perpendicular line. Okay. So right angle to this line, you have to draw one line from I. Both will be intersect at Y. So that is the point of intersection. Okay. So now all the component we have included. Fi you can calculate from the formula. Okay. And Wc that is given in the problem, because mass of the connecting rods is given, it will be acting downward direction. So based on that, extend that line from I, draw one perpendicular line, you can get the point of intersection Y. And Fc you can calculate through this drawing procedure. Okay, so the directions you can find out, and the perpendicular distance from I, that you can get the value. So x you can calculate. So this is the Wc. And you know Ft, that is torque force or the tangential force. Okay, that is thrust force acting on the crank pin. So that will be acting right angle to the crank. Okay, so this will be the final component that also acting on the crank connecting rod. So we have to include this. So based on this, you have to find out all the values. So these are all some of the formula. Acceleration of the PO, that is piston with respect to fixed point, we can calculate by using that Klein's construction formula, omega squared into the link length OP. Okay, so that is given. So that is should be equal to NO in that component. Acceleration of G with respect to O, that should be equal to OG vector. So omega squared into GO vector. Acceleration of D with respect to O, that should be equal to DO vector. Okay, so omega squared into DO. The inertia force Fc, the component may be given as the theoretically you can calculate Fc is equal to NC omega squared. That should be equal to mass of the connecting rod omega squared. You can find out if the speed is known. GO vector, that is a resultant force if it is acting through G. If you measure the distance, you can get that value. Substitute it there, you can find out the value. Theoretically, we can calculate this. And what are all the other components that are acting? Fi, that is acting opposite to the PO, opposite to the net force Ft, and Fn normal to the piston movement or slide bars, along the slide bars, and weight of the connecting rod downward direction. Okay, inertia force parallel to OG vector and through the point of intersection at E. Then Fr parallel to crank and opposite direction, and Ft perpendicular to the crank. Now this is the formula to find out the component Ft. Ft you can calculate. Ft is the required component because Ft into perpendicular distance if you put, you can get the torque that are acting on the crankshaft. That is our aim. So Ft you have to calculate. So other value you can find out. So Ft into perpendicular distance IC. Okay, Ft right angle component you have to measure. So the distance between C to I if you measure, that is the perpendicular distance. With respect to I you have to calculate all the values. Then Fi, that is acting opposite side, perpendicular distance IP. Fc perpendicular distance you can calculate. Okay, WC and